Hello everyone, my name is Jerry Salen and I'm the CEO of Nails Engineering Services, and today I'm going to be talking about the impact of process intensification on process safety. Process intensification can take place in many different industries, but today we're going to talk specifically about the chemical process industry. It can also take form of many different improvements. Today we're going to focus on heat and mass transfer. Process intensification has been known to show benefits in the areas of reductions in capital costs, energy savings, raw material costs, improving the flexibility of the process, reducing the inventory, looking at lean manufacturing principles. It can also improve quality and get a better environmental performance. But the emphasis today is going to be on process safety. During traditional scale-up with batch or semi-batch reactions, we typically have the same tail where we start with a very small working volume, like an EasyMax system, where we're using test tubes for screening of reactions, and even using the EasyMax 100 ml reactor to gain some heat flow profiles, understanding what's going on with the reaction. And once we understand what's going on with the reaction, we need to get process safety data. That typically involves using the RC1 reaction calorimeter to understand the main reaction's total heat output in the heat flow profile. That allows us to safely scale up to the kilolab and production quantities. There's also a second part to this, which is the undesired reactions that can occur in the case of a runaway. We're going to discuss those next. We'll start by examining a cooling failure scenario, and this figure was adapted by a figure that Dr. Rudy Gayax had developed in the referenced article. Keep in mind that this figure outlines two distinct levels. The first is the desired reaction, which is highlighted in the blue area. This is what most scientists see in the laboratory. If you observe the undesired decomposition reactions, which are highlighted in the red area, most likely something has gone wrong. To fully assess the process safety of the system, we have to study both the desired and undesired reactions. Looking at this scenario of cooling failure, we want to understand the degree of violence and the potential for thermal explosion. And that can be examined and quantified by looking at the adiabatic temperature rise. So we have several categories: low, medium, and high. Low being less than 50 degrees adiabatic temperature rise. Medium being between 50 to 200 adiabatic temperature rise. Then if you get much above 200, that falls into the high or critical or catastrophic categories. So we get these values, the adiabatic temperature rise, we can calculate those from the RC1 experiment. And it's a calculation from the heat of reaction divided by the heat capacity of the system. Then we can calculate the maximum temperature of the synthetic reaction, which is very important. It's basically from the process temperature, we add in the adiabatic temperature rise and we get the MTSR. And that becomes critical when we start discussing the decomposition reactions. When do those decomposition reactions occur? And we can get that data from DSC and ARC, accelerated rate calorimetry. This is not all inclusive, but it gives you the background of what we're looking at for severity. The probability can be evaluated using the time scale. And what we're looking at this point is, if the cooling failure were to occur, how long would it take for you to implement a solution, fix the pump, fix the chiller, so that you had cooling back online again? This ultimately boils down to how much risk you want to assume. The time to maximum rate under adiabatic conditions is the hours you have prior to that reaction mixture starting to decompose and rise in temperature. And that's measured by the adiabatic temperature rise of the decomposition reaction. So there's a lot of things you have to consider, many questions you have to ask during this runaway scenario. What happens if you lose cooling? Will the reactor warm? If it does warm, what temperatures are critical? If I do reach these critical temperatures, how long do I have before something catastrophic will happen? Will something catastrophic happen, or will it just be a quality issue? We have to put ourselves in that specific scenario and determine the best solution. At this point, we have the majority of the data we need to assign a criticality class, which is shown here in this stoplight chart. So we have our process temperature, the TP. We have our maximum temperature synthetic reaction, MTSR. We have our maximum temperature for technical reasons, which is typically the boiling point. And we have our TD24. the decomposition temperature. So we match up our process variables, process values, and we see which criticality class we land in. And depending on the criticality class, there may be some engineering controls or procedural controls we have to institute to make it for a safe process, make it for a safer process. The question always is asked, what happens if you are in a criticality class 5 or a 4 or a 3? What to do? Well, if you're in a criticality class 5, there's no safety barrier between the main and secondary reaction. That's a very scary place to be. So you do have options. You can dilute the system. You have a bigger heat sink in the reactor to start with. You can always go semi-batch where you limit the reactive reagent or substrate that's being reacted, or you can go continuous. We're going to talk about the third option, which is going continuous. Now we finally enter the meat of the presentation and discuss the actual application and case study, where we're making these Alkyl NENAs, these nitrate ester nitramines, and they're plasticizers. They're used to plasticize materials that are used in rocket propellants, gun propellants, or explosive compounds. In this particular process, we're using an alkyl ethanolamine and nitric acid at low temperatures. And we get these two intermediates that we can monitor and watch their rates of formation. When we first started, these rates were unknown, and the ratios we were not sure of. But you could either form the nitrate salt of the amine, or you could form the nitrate ester of the amine. And you also produce water, which becomes critical in our assessment. So the question was, could the Corning Advanced Flow Reactor intensify this process because of the large amount of heat that's given off during the chemical reaction? More specifically, could the Advanced Flow Reactor handle the large amount of heat being generated and remove it at a rate where the temperature would not increase? And could its enhanced mass transfer handle the viscous material that would be very challenging to mix at larger scale if we went with the batch route? Could the Advanced Flow Reactor assist us with process intensification of the NENA process? Just to complete the story, I'm going to show you step 2. We're not going to get into too much of the details of step 2, but after step 1, we dehydrate the system with acetic anhydride, removes the water produced from the nitration, and allows the nitration to further carry on, where we make the nitramine as well. This reaction used to be a one-pot process where the amine was fed to not only the nitric acid, but a mixture of nitric acid and acetic anhydride in the presence of the acetyl chloride catalyst. When they ran that, they had a very exothermic reaction, and it appeared that some of the amines were not compatible with the acetic anhydride, which resulted in fires. This two-step process actually separates those out so that you first form the nitrate ester, then you form the nitramine, giving you the nitrate ester nitramine or the NENA compound. Here we examine some of the patent literature that's out there, and it's a bit scary. It says the addition of the amine must be effected below the liquid surface to avoid spark spheres, which we weren't sure what a spark sphere was when we started the project, and this was years ago. And it further says, controlling the rate of addition, amount added, and sufficient cooling of the reaction flask is thus of great importance when alkyl ethanolamine is added to nitric acid. And then finally, at larger scale, 100 liter, 1,000 liter or larger, the reaction step is expected to be particularly dangerous. So we had the warning. Most likely they ran into some challenges when they were scaling this up. We turned to the continuous process, and we thought the Corning Advanced Flow Reactor would be ideal for this because of its ability to give great mass transfer and heat transfer, and it's scalable. So the previous slides went into the details about looking at criticality class and assignment and how we go about doing that. So we're going to apply that methodology to our NENA reaction. One thing that is a little bit different than what we've discussed so far is sparking. We've seen sparks before in batch reactions, including the NENA reactions, and then generally attributed them to hotspots being formed at the interface of the substrate and it's being nitrated in the nitric acid. So we would study this and see if there's anything we could do to mitigate it. So the first part of our thermal hazard assessment was using the RC1. We love the RC1. It can rip out 6,000 watts per liter. And we were able to obtain heat flow data using a nice long dose over time, avoiding higher temperatures and decomposition. You can see the dose was paused a few times due to the safety settings for the TR. This data was a pleasant surprise because it showed us that we were dose controlled at the beginning of the reaction, and it appears that when the dose is stopped at the end of the reaction, the heat flow ceases. So that's good to see. We like this data because it shows very little accumulation, and combined with the offline analytics that showed there was complete conversion of the amine, we were very satisfied. Here's a short video clip showing the violence that we observed in the 500 ml reaction when the amine was dosed to the fuming nitric acid. You hear these pops and cracks. Gas was visibly generated in the headspace. Typically, if we were attempting to see kinetics, we would attempt an all-at-once addition of the amine, but we decided to take a much different approach based on the initial data. This was just a little too hot. This is where we turned our attention to microfluidics. It offers excellent heat transfer and mixing. It is just what the doctor ordered to solve this challenge in our form of process intensification. The system for the first step of making the NENA is a bit viscous, and so we were starting off in the G1 Advanced Flow Reactor, and what we found was, I'll show you a short video here, is that when the amine dose was only roughly at 25% of the total dose required to meet our requirements, we started seeing little bolts of lightning, tiny bolts of lightning flashing. If you look closer, if you can zoom in, you can see gases being generated and these gases being ignited. This is not desirable and not what we wanted to see happen. And it actually ended up with the plate fracturing from overpressurization. The good news was it was one plate, it was 10 mils working volume. We were able to swap that plate out, put a new plate in, and get right back to work in solving our challenge and what was going on with this reaction. So we progressed to part 2 of our thermal hazard assessment, looking at the decomposition reactions. As you can see here in our board, we had total heat measured in kilojoules per kilogram was greater than 500. It was in the critical area. The adiabatic temperature rise was greater than 200. The MTSR was greater than 250. TD24 was less than 30 degrees Celsius, and our process temperature was 5 degrees Celsius. All in all, it gave us a criticality cost of 5 going forward, pointing us in the right direction, which was continuous processing. So going continuous doesn't really take us out of the criticality class. What it does do is offer us the opportunity to significantly reduce our reactive inventory from, say, a 100 liter, 1,000 liter, 2,000 liter reactor down to a 10 mil microfluidic module when using the G1 Advanced Flow Reactor. So I'd like to do a quick summary of the step 1 thermal challenges. We had issues with the initial addition of the alkyl amine that included sparking, which was not anticipated to be so destructive, so violent. The reaction was highly exothermic. There's significant gas being generated, which is impacting the ability for the system to cool, but also those gases appear to be flammable and ignite within the microfluidic module. So the question became, is this actually suitable for the AFR, or do we need to turn to some other technology? This might be just too intensive for the AFR. We also noticed that the amine, it was a viscous liquid. We got poor heat transfer, especially when the gas was present, displacing the liquid. That's a big challenge that we have to solve. We think we saw some hot spots prone to be forming right at the addition where the amine meets the nitric acid. And we also noted that the flash point of the Alkyl ethanolamine is rather low and could possibly be reached from the hotspots. So in final summary there, we have the reaction can be hot enough to locally vaporize and ignite this gas. And we witnessed that. We broke a plate. And so we had to go back to the drawing board and figure out what was going on and causing this to happen. If you've seen any of our previous webinars, you know we love using in situ tools. And we always monitor reactions using our in situ spectroscopy. You can never know what you're going to see. It can be very frustrating to have such great tools sit idle. So our philosophy is that if you're going to run the reaction, put the tools in there, see what comes out. Sometimes it's very telling, other times not so great. But this reaction gave us tremendous insight to what was going on and highlighted our path forward. For simplicity, we broke these telescoped reaction steps into two for analysis. So here I'm just showing you the waterfall plots as a function of time, and the amine dose and the acetic anhydride dose. And we're going to dive into those a little bit deeper. First thing I like to do is turn on concert and see what concert predicts and see what kind of profiles if they're believable. So we saw this blue peak that grew in and went away during the dose. So that could mean a lot of different things, but it definitely looked real. The peak looked real. We also had this nice green profile, which has a little bit of a delay, but it falls along with what we think is like an intermediate in the blue guy. And then all of a sudden it changes trajectory and grows in for the rest of the dose and then ceases at the end of the dose. Both the blue line and the green line are pretty constant at the end of the dose. So now we have the heat flow profile and we have some spectroscopy data. We're going to overlay these and see if something jumps out at us. So in this slide, we show an overlay of the heat flow profile, as well as two of the concert profiles we discussed earlier. The pink profile, we think looks like what could be the nitrate ester, and the green profile, we think could be the nitrate salt. And if you think about it, sequentially, we're going from the amine to the amine salt to the nitrate ester. And as the reaction starts off, there's no water present in the nitrating media, so you have enough nitrating power to make the nitrate ester. And as time goes on, water builds up, the nitrating ability is decreased, and so now you start seeing the nitrate salt growing in because the nitrate ester is not forming any longer. So we take this a step further in the next slide. What we did here is we applied a correction factor to eliminate the dilution of the amine dose it impacts the ester. So it looked like it was going down, but it really isn't. It's just the intensity that's being diluted from the addition of the amine. So now we can look and see this nice pink curve. This makes a lot more sense. We start off by making the nitrate ester, and then at some point, the nitrating ability of the media has been decreased because of the water that's been present. And now you start forming the amine salt, which is the intermediate between the amine and the nitrate ester salt. Now it all makes sense, and we have some ideas of what's going on. So the violence that's occurring is in the formation of the nitrate ester. That's what we suspect. And so this is great for a qualitative tool, but we want to get some more quantitative data, and so we turn to flow NMR. Our flow NMR system is excellent for tracking species in solution. It's also excellent for getting quantitative data really quickly and now in real time. So we have our EasyMax system set up in a fume hood, and we have a pump that circulates from the EasyMax into the magnet, and we can get quantitative data real time. So this data made it clear that we make the nitrate ester immediately. We see the rate of formation of the nitrate ester decrease and the amine salt grow in. We didn't understand why initially, but it makes sense that the nitration generates water. The water dilutes the nitrating agent, weakens its ability to form the nitrate ester. However, in the next step, when we dehydrate the system by dosing in acetic anhydride, as you can see here, we see the nitrate salt is consumed and the nitrate ester forms, further confirming that's what was going on. This is great information for us to have while in the design phase of the project. We now know the reaction is violent to start, sparks, it hisses, it's extremely hot. We know it tends to calm down over the dose. We do not have to be Sherlock Holmes here to see the stability brought to the reaction when water is present and only the nitrate salt is formed. We want to use this to our advantage. So we came up with a new plan based on the data that we had so far, and breaking this up into basically 3 reaction steps and using water to decouple the amine salt and the nitrate ester. So step 1 was using dilute nitric acid. We avoid the nitrate ester altogether and the violence associated with it, and we reduce the heat of reaction, avoid those hot spots and sparking. So we make the amine salt. Then we'll go back to the dehydration of the system using our acetic anhydride, and we'll form the nitrate ester salt. And then finally, we can then turn to the NENA formation just using the existing conditions, more acetic anhydride, put the catalyst in, the acetyl chloride, and you'll form the alkyl NENA. So that was the plan going forward. We just had to prove that it would work. So we were back to the RC1. We were pleasantly surprised when we ran the reaction that there was no more hissing, there was no more gas generation. Here we show the overlay of the heat flow for the concentrated acid versus the dilute acid. The concentrated acid starts by forming the nitrate ester, while the dilute acid only makes the nitrate salt. This was confirmed with our spectroscopy and also NMR. The maximum watts observed is significantly reduced with the dilute acid, and we were able to control the chemistry to our liking. This was actually great news, and it was back to the flow setup. We were able to do some quick modifications to the G1 setup and successfully demonstrated step 1, producing the nitrate ester without the undesired violence. Notice that we split the feed of the amine to reduce hotspots and avoid temperature rise. We're also able to break the system into 2 temperature zones, which is nice because these modular systems, it's easy to tailor multiple feeds and temperature zones. So if you want, you could start off at a lower temperature and allow it to warm for step 2, for example, and flow into another set of microfluidic modules. I'll just give you a brief description of these plates. And plate 1, we have the nitric acid feed being put in, and it's pre-cooled, and the amine feed as well being pre-cooled. Then we have some mixing plates where we get residence time and contact between the acid and the amine. That's where we were seeing violence, but no violence occurred during these reactions. And then we have a second amine pre-cooling plate, and then a second mixing plate. And then we introduce the acetic anhydride, which dehydrates the system and allows us to progress even further to the nitrate ester. This can be tailored and even allowed to add the acetyl chloride with a catalyst and proceed on to step 2, which we eventually did. So this video is a side-by-side comparison showing we went from a gas generating, sporadic feed, violent sparking, to a really well-behaved system with similar feed rates. The only difference being the dilution of the acid reduced the overall percentage of the amine in the first mixing plate. But we had the process understanding and the safety, and it really wasn't that much of a big change because we had the second amine feed to make up for it. I think this slide really summarizes what Nailus is all about: the chemistry, the analytics, and the chemical engineering. We took a process that had some challenges with sparking and violence, and we understood the chemistry using our analytical tools like flow NMR and the in situ tools like the in situ spectroscopy, the Raman. Also used IR on this as well. And then using the chemical engineering for the heat transfer and the mixing provided by the Advanced Flow Reactor. I think it's really a culmination of process development using all these tools. And you can't forget the people that worked on this, making those decisions and those discoveries resulted in an excellent process that we were able to present to you today. So we've come to the end. We're at our conclusion slide, and I hope this is a good example of process intensification and some of the challenges we encountered and how we mitigated those using the various tools and equipment that we have at our disposal. We had a nice exothermic reaction, and it was coupled with rapid kinetics. Low flash point resulted in sparking in the Corning AFR. We had a combination of in situ Raman and flow NMR, which allowed us to really gain process understanding and even quantitative data when we decoupled these reactions. It turns out that controlling water content was able to decouple the heats of reaction between the formation of the nitrate salt and then the further to the nitrate ester. We also were able to reconfigure the Advanced Flow Reactor for successful continuous production of the NENA compounds. So with that, I will say thank you for listening and open it up to any questions.